to start with?
London dispersion.
Okay. I heard London dispersion first, so let's go through it. What do we have for London dispersion?
I know it's very weak in comparison to the other ones.
So in comparison to the other ones, we could go through and say very weak. I would argue we could just throw in the est. We got that covered with less words or less letters. So it's the weakest. What other information? What do you got? Okay. Comes from non-polar covalent bonds. What else do we have? Everybody know what weakest means?
Most easily broken.
Lowest amount of electronegativity.
Okay, I wasn't even going there, but okay. So if someone went up to you and said, you're weak, they're saying you have the lowest amount of electronegativity?
Smallest amount of polarity.
Someone comes up and says, you're weak, they're saying you have the smallest amount of polarity? You're not strong, okay? So if we're saying it's weakest, we're saying it doesn't have a strong force. It has a weak force, okay? A lower energy, okay? We'll deal with that number in a second, okay? So in theory, we do know what weak is, right? We get the idea of weak versus strong. Where I was going with that was in the next part of it. Does everybody know what a nonpolar covalent bond is?
Yes.
Yes? Okay, so 2 people shook their head yes. 3 people. The rest of the class saying you don't know what a nonpolar covalent bond is. I got at least 1 person being roughly honest, at least 2 people being roughly brutally honest and saying no, that's good. Okay, we need to acknowledge our weaknesses. So those that said yes, what is a nonpolar covalent bond? The silence is a bit disturbing when we just have people say yes, they knew exactly what that was. What is a nonpolar covalent bond?
I could recognize it, but I can't.
Okay, so that was something that we could write. We could provide an example. An example is something that you can work with. If all you remember is an example for each of these, when you get to the exam, you could take your example knowledge and compare that to answers. That is valid information. You should hold that. Okay, so what was your example?
I can put an example, but I can make one.
Okay, while you're thinking of an example,
Covalent means the same one to the same one. Well,
nonpolar covalent means
same one to same one, but covalent means it's going to be 2 non-letters.
same atom to same atom.
They're working
Okay.
as a team somehow. I can get that from the language because this is code.
So,
Sure.
So like an example that I did find was the team example you're on, but
Yep.
it's a C with a dash H and then it has the bond with the
So-
dash C.
A bond from carbon to hydrogen does not fit the definition of same atom to same atom. So while I like your example, it's a phenomenal example, and it's probably the most important example when it comes to London dispersion forces. Okay, so that is incredibly important, but that doesn't fit this same atom to same atom. It's not really an exception, it's an and carbon to hydrogen. Those 2 things are classified as nonpolar covalent. Okay? Is there another definition to help us define nonpolar covalent? Someone started to hint at it, so yes, there is one. What did I tell you to I told somebody to because they started to mention something, and I said I didn't want to look at that yet. The 0.5, there's the 0.5. What is this 0.5? It is the difference in electronegativity between the 2 elements. So our difference we show as a delta. Electronegativity is the, I believe, Greek letter chi. If that difference is less than 0.5, by definition it is a nonpolar covalent bond. How many of you know the electronegativities of any element on the periodic table? That definition then sucks. Okay? Because you will also notice in that I didn't raise my hand. Okay? I don't know the electronegativities either. But we should know general trends, where fluorine is the most electronegative, and cesium or francium, depending on how you want to look at it, is going to be the least. Okay? So electronegativity increases to the right and up. So we could look at approximations of differences in electronegativity to help us define this. Okay? Even then, the exact numerical differences we aren't going to be able to nail down. That's why we come up with the rules of thumb listed underneath. Same atom to same atom. If I see fluorine, it's the most electronegative atom, I would probably predict it to be a polar compound, not nonpolar. How does it become nonpolar, being the most electronegative? Delta meant change, a difference. So the difference in electronegativity. Fluorine is one of them. How do I make sure that difference in electronegativity is less than 0.5? What should I bond the fluorine to? Fluorine. And now the difference is 0. Is that less than 0.5? Yep, same atom to same atom. Okay. The next one, carbon to hydrogen. The carbon to hydrogen difference in electronegativity is relatively small, but again, nobody wants to memorize those. So why do we just say memorize carbon to hydrogen as being nonpolar covalent? Because carbon to hydrogen bonds show up in a lot of different places. Okay? All of us are composed of carbon to hydrogen bonds. Okay? Because of their massive prevalence, we just memorize that as a nonpolar covalent bond. That allows us to draw some interpretations pretty quickly. Okay? Another definition that I heard shouted out, because it just says same atom to same atom, these are nonmetals to nonmetals. Okay? Any other information we could throw in there? I'm a little leery of the sharing of electrons aspect. I know the intent behind that, but it can be a bit dicey, so I tend to avoid that. How many people had all of that information on their sheet of paper? All of that? Seriously? You remembered all that from the video?
It's right there. Wait, what?
No. Not after I wrote it on the board. Oh, come on. No.
Slow that down. Watch the video if that means anything.
How many of you remembered all of that to be able to write that down? No. Okay. So this is one of the things that you have to acknowledge. Your recall memory of that is weak. You need to practice this so that you can have that content at your fingertips. That is a lot of content to have to try and memorize and hold on to. So of those things, we might want to try and decide what is useful and what is not. Okay? How many of you want to memorize any electronegativities? Okay, so is the difference in electronegativity a useful thing to memorize? No. Did some people have it memorized in here? I didn't tell you that number. At least one person had it memorized. That's cool. Why? We're very number-centric. We want to memorize numbers. Okay? As we talked about in the previous units, numbers are useless without the meaning associated with them. Numbers don't do you any good unless you have units. So make sure you're including your units. In this case, that number isn't going to be useful because you won't use it at all. So we should ignore that as information. Okay? It being weakest, that's going to be incredibly important. Okay? Recognizing that it comes from nonpolar covalent bonds, that's important. Okay? But do I know what a nonpolar covalent bond is? Just as a statement, not really. So what might be more useful is not memorizing nonpolar covalent bonds, but memorizing what those are. I'm going to see London dispersion forces as the weakest intermolecular force when looking at a compound that is same atom to same atom or carbon to hydrogen bonds. Make sense? So you need to be able to evaluate each piece of information and decide, is that worth you memorizing or not? That takes time and that takes practice. Okay. What's the next one you want to look at? Actually, I'm on. No. What's the next one you want to look at? Dipole, dipole. Okay. We can do that.
We're talking about being diaper. It's probably not right, but that's what I think.
Probably not right. Was there actually a question in your mind? Diaper, diaper. Might not be right. As in, it could possibly be right. Just asking. So everybody's going to remember diaper, diaper. Okay. Dipole, dipole. What do you have on dipole, dipole? Okay. It is a polar covalent bond. Okay. Which happens to also be non-metal to non-metal. So right out of the gate, what can we do? How useful is it going to be to memorize non-metal to non-metal?
Pretty useful.
If I give you a non-metal, non-metal bond, which force are you looking at? Dipole, dipole? It could be London dispersion. Is the definition of non-metal to non-metal particularly useful? No. We could easily get that confused between two possible answers. Okay? You could make the argument that yes, you're whittling that down from 4 possible choices to 2 possible. Okay? You're getting right 50% of the time. That's where the rest of the information can come into handy to help differentiate. So maybe we don't want to look at non-metal to non-metal because that information duplicates. What else could we look at for dipole, dipole? What do you have written? I would argue the dipole, dipole, by the way, is one of the hardest to deal with. What do you mean kind of weak?
It's not the weakest and it's not the strongest.
Okay, it's not the weakest. Okay? So we could say it's stronger than London dispersion. Okay? But we could also add it's weaker than everything above it, which would be hydrogen bonding and our electrostatic, right? Does that make sense? Now, that's a lot of words. That's kind of rough, but hey, that works. We've got some parallels that we could run too. I mean, we have information down here, so we've addressed the type of bond. Non-polar covalent, polar covalent, cool. We address weakest, stronger versus weaker. Did we talk about a difference in electronegativity yet? Oh, you didn't bother to memorize that one. Because why? The cognitive overload on those numbers. Uh-oh, you just raised your hand. Does that mean you've got the number? Ah, you guys suck. And by suck, that's actually pretty good.
0.5.
So what he meant was you're doing a good job.
0.5.
1.7.
Good job. Hats off.
The fancy shapes too for electronegativity.
Oh, nice. So, again, electronegativity. You've got the number. Is that a useful thing for you to memorize? Okay? So, and that's hard because we're going to go, oh, I've remembered this thing. You have to now do that extra piece of thought and be like, was that thing actually useful for me to memorize? If it wasn't, you need to start to try and wipe that from your brain because that's holding space where you aren't going to be able to put more information. Okay? Make sense? Okay, so we've got that difference in there. The other thing that becomes problematic with this difference is that 1.7, depending on who you talk to, changes. Same with the 0.5. Yeah, which sucks. Okay, so again, probably not the most useful. Okay, what else could we reference? We've got the London dispersion as a model. We've addressed weakest. We've addressed the type of bond. We've addressed the difference in electronegativity. Non-metal to non-metal, we got that. Do we have an example of a polar covalent bond? Sorry, a dipole-dipole compound? Okay. A suggestion that got thrown out in the last class too would be OH. technically that would qualify, but we're going to say no for the moment. So that does not qualify as a good polar covalent example. So give me another example. I'll accept CO2. It's a little bit more complex because you're looking at a larger structure. Really all we want is a single bond. So just CO, right? Okay. So the CO bond would qualify as a dipole-dipole. So when we look at CO2, what are we bonding? Carbon to oxygen. Well, isn't that what this is? That's going to get us a dipole-dipole. Does that make sense? So we want to, again, simplify down as much as possible so that we can scaffold up indefinitely. If we only pick a compound like CO2, what happens if I look at something that's not O2? Okay, and then it becomes a little more challenging. Make sense? Okay. Last thing we could address for the nonpolar covalent, we did come up with some examples, right? Same to same and carbon to hydrogen. Did you guys give me any examples for polar covalent? No, no, you didn't. That's kind of rough. Right? We're looking at a large difference in electronegativity, right, that doesn't involve hydrogen. So if we see oxygen, let's draw a pen, oxygen, nitrogen, carbon, fluorine, chlorine, phosphorus, sulfur, selenide, bromine, iodine. God, that's a lot of things to have to memorize, isn't it? What's your little hand?
Can't you just memorize it as everything else?
In the slide, I actually say that it's easier to memorize it as something else. In fact, all three of these things can fall under one big category, one big umbrella. Everything else. Okay. What is everything else in reference to?
Anything that isn't the ionic, electrostatic, hydrogen bonding, or London dispersion.
Okay. The dipole-dipole is not the one that I wanted to start with. You guys went that direction, so that's cool. The reason why I didn't want to start with it is that the easiest way to define dipole-dipole is to acknowledge that it is not a London dispersion, it is not hydrogen bonding, it is not ionic. Why? All of the possible elements that could potentially show up in that compound. That makes it insanely difficult to have to deal with. Okay? Too many different floating pieces. So if you can simplify and just say, well, it's not one of the other ones, you're okay. Does that make sense? That would also apply with the stronger and weaker. It helps you to decide, well, it's not as strong as ionic, because it's not ionic, and it's not London dispersion, which means it's somewhere in between. So if you can establish your caps, you know the middle. Make sense? Okay. Which one do we want to look at now? As a hint, if you say hydrogen bonding, I'm going to say no.
Hydrogen bonding.
No. What do we want to move to now? What's the only other one on there? And polar covalent isn't on there. The ionic or electrostatic. So, how do we know we have ionic or electrostatic forces? Ionic bonds. Anybody notice something kind of stupid about the naming system we've got here? We have an ionic force and an ionic bond. They're both called ionic. So we could get those two concepts easily confused. Okay? They are the most difficult to differentiate from each other because it depends on what system you're looking at. So you have to be careful in differentiating those. So ionic electrostatic forces will come from ionic bonds. What else do you know? Okay. Metal and a nonmetal. So again, matching after the pattern of stuff you already have. What do I have? Okay. Is that something that's useful to now memorize? Why? It's the only one that has metals. So if you find a metal, what do you have? An ionic compound. You've now very quickly whittled out your possible answers and you're looking at an ionic force. Okay, so yes, that's going to be hugely important to memorize. Memorizing an ionic bond isn't all that useful because what is an ionic bond? It's a metal to a nonmetal. So we have some useful information. What else? It's the strongest. Do we need to further define our nonpolar covalent bonds? Like down here with our London dispersion, we said nonpolar covalent. Here we said polar covalent. We said metal to nonmetal, and then we said same atom to same atom on carbon and hydrogen. Do I need a further refinement other than metal to nonmetal? No, that covered it. Okay? We've got weakest. Ooh, we have a difference in electronegativity. We address what that one is? For those of you with those good friggin' memories?
1.7.
Our difference in electronegativity needs to be greater than 1.7. Okay, again, not super useful. It's not bad. You got something. Trivia. Cool. What else? You got nothing else? That's cool. You don't have anything else. What was carbon to hydrogen? What was oxygen to carbon? What were those? Those were examples. What should we do for the ionic? Let's have an example. What example do you want to look at? Sodium chloride. Why'd you pick sodium chloride? The one you remember. Sodium chloride we deal with super commonly. We know sodium's a metal. We know chlorine's not. That fits our definition. The example will help us get those definitions. So if you can memorize the examples, that can help you process of elimination through multiple choice answers and potentially even get you legitimate writing down of what those things mean. Make sense? Okay, I think we covered all the basics on that. Yeah, which gets us to hydrogen bonding. Why leave hydrogen bonding out of this?
Because it's unique.
Hydrogen bonding is sort of unique. I would argue it's not unique. Hydrogen bonding is the same thing as a dipole-dipole. One and the same. We have a difference in electronegativity that falls between 0.5 and 1.7. Hydrogen bonding is slightly different though. That difference of electronegativity does not dip as low as 0.5. It stays up hovering around the 1.7. If the difference in electronegativity hovers that high, what could you say about the strength of hydrogen bonding? It's a really strong dipole-dipole. It is so strong that we as scientists said, you know what? I'm going to create its own category. I'm going to call attention to it so that when I see this show up, I know it's strong and I know it has a larger impact than the average dipole-dipole. Okay? You could look at hydrogen bonding as like a plus in a grade system. Right? You could have a B or a B plus. Hydrogen bonding is that B plus. Make sense? Okay. So it is a dipole-dipole. What other information do you have about it? This would be one of those let's break down the name of it things, moments. Hydrogen has to be involved. Okay? Because the difference in electronegativity is darn close to that 1.7, that hydrogen needs to be bound to what? So if we look at the periodic table, where is hydrogen on the periodic table? The upper left. Or is that a hand, or are you telling me?
I have a hand from like this, from what you're talking like page
Okay.
down to your point.
Yes.
Since it's higher, it has to belong to something on the right side where it would be lower, and the video, it only talked about three, fluorine, oxygen, and nitrogen.
We're talking about a difference in electronegativity that's huge. If hydrogen's to the extreme left, okay, that's on the lower end of the electronegativities. So I need a very high electronegativity, which means moving to the upper right-hand corner, which nails us down to, oh geez, hydrogen 2, fluorine, oxygen, or nitrogen. Just like girls, hydrogen just wants to have some fun. Actually, wasn't too bad. Don't worry, it's been a lot worse than that, but that's the best one I got. Does that make sense? So to have hydrogen bonding, you must have a hydrogen bonded to fluorine, oxygen, or nitrogen. What, you not get that one? Don't worry about it. It's a horrible, horrible joke. Ouch. Well, that's probably fair, to be fair. Yeah. So, hydrogen bonded to fluorine, oxygen, or nitrogen. So this is a common one. Hydrogen. Would I expect that compound to be hydrogen bonding? It has a hydrogen and it has a bond, so it must be hydrogen bonding. No, because carbon is not fun. Hydrogen to carbon would be our London dispersion, because hydrogen to carbon is by definition a nonpolar covalent bond. Okay? So our example for hydrogen bonding, our example bond for hydrogen bonding would be hydrogen to oxygen, which is why I said I didn't want it for the dipole-dipole. It is officially a dipole-dipole, but it's a special one. Okay? The next part is we could reference the strength. It is stronger than the dipole-dipole. Okay? Some of that's kind of embedded in there because fluorine, oxygen, and nitrogen are the three most electronegative elements on the periodic table. So that's going to generate one of the largest differences in electronegativity. Okay? Kind of makes sense? All of that information is something that you should have at the back of your head so that when you see questions about intermolecular forces, you can answer them. Which brings up the question of what could you see? More than likely, you aren't going to be given the compound sodium chloride, what is its force? It's not going to happen. You have to be able to apply your knowledge to what does that mean about that compound. And that's where it can become very, very difficult. Okay? Questions about what those forces are. Okay. As we went through and did this, notice that we also called attention to the types of bonds. A polar covalent or non-polar covalent bond came from London dispersion. Okay. Polar covalent bonds were dipole-dipole. Hydrogen bonding is dipole-dipole, which means polar covalent bond, and ionic forces generated from ionic bonds. Okay? So if we can figure out the bond, we know the strongest force. Once we know the force, we can start to apply that knowledge forward. Make sense? Okay. Which gets us to this figure. Okay? Ultimately, this figure should have another layer to it. Remember when we talked about physical and chemical changes? We had that kind of rainbow thing where we said physical was over here, something like that, and chemical was over here. And we said, well, what happens if salt dissolves in water? Is that chemical or physical? That was a gray area. Salt dissolving in water on this spectrum is probably somewhere dead in the middle between those two. So depending on which definition you want to use, you're going to slightly bias your opinion to calling it a physical change or a chemical change. Okay? So when we talked about chemical and physical, it's not black and white. There's a big gray area. Guess what happens with forces? There's a really big gray area. It's much the same thing. Really what we're looking at here is that same diagram as a big line. Okay? Except at one end of it, we have a strong attraction. And at the other end, we'd have a weak attraction. And this is an attraction between any two atoms, period. I don't care where they are, any two atoms. If that attraction is really, really, really strong, I'm going to define that attraction by a new name. I'm going to call that name I'm going to call it a bond. If I have a really strong attraction between two atoms, they are now a bond. Okay? So I'm going to cut my thing in half and say, well, I have bonds. And I have forces. Okay? Well, that attraction is because they're sharing electrons, or they aren't sharing electrons. If those two atoms are equally sharing electrons, they're now strongly tied to each other because they need each other's electrons to stay near each other. That would generate a different kind of bond than a bond where maybe they weren't sharing electrons. So because of that, I differentiate those two bonds types. What do I differentiate them as? Two different bond types where they're equally sharing electrons versus not sharing electrons. There are some bond types listed on the board. We have ionic, and in an ionic bond, are they equally sharing electrons? No. How do we know that? They're ions. They're charged species. So we have ionic bonds. They aren't sharing. That's not a strong attraction. Okay? What about the other end of it? Instead of being ionic, we could have covalent. And arguably, we should call that, which isn't officially on here, non-polar covalent, because they're equally sharing electrons. There's no polarity associated with it. So we have non-polar covalent. Is there a gray area between equally sharing and not sharing? Yeah. What do I want to call that weird gray area in between? Okay. I could call it everything else. Everything else is too general of a name. That's where we drop in polar covalent. We now have our three bond classifications. Okay. What if you were a bond, let's say a little blue star, that fell right there? Are you polar covalent or non-polar covalent? I don't know. It's in the gray area. Okay. Its properties will be similar to a weak polar covalent force or polar covalent bond, or it'll be kind of similar as a weak or a strong polar covalent bond or a weak non-polar covalent bond. So we'll see a mix of properties. Okay? The idea, though, is we can see this segregation in that interpretation. Okay, what if we have no attraction between the particles whatsoever? They're like, nah, I don't want to see each other. Would that be a really strong attraction or a weak attraction? Weak. We said it was 0. Can't be strong, so it's got to be weak. It is so weak that when we first identified these kind of spectrums on it, we said, I'm going to ignore it because it's that weak. Turned out we were wrong. It is actually kind of important, and it does contribute. Right? Because someone went through and said, well, no, actually, you're wrong. It is important. What do they get to do? They get to name it after themselves. Hence, we hear van der Waals forces. Okay? I don't know why we call them London dispersion forces, but that's where van der Waals is coming from. Van der Waals was the guy that put it together. Okay? There are a variety of other names that can sometimes make more sense for them, but what those are now an exceptionally weak attraction. So we could put those down there. What if there's a stronger attraction between them now? We're getting a little fun with colors, why not? Why would I have a weak attractive force? Okay, what we're talking about is effectively relationships. Okay? What might you predict my attractive force is with other people? Little, weak, why? Because I'm married. I already have a strong attractive force to somebody else. Okay? I'm already a non-polar covalent bond. We're already sharing everything, which means my attraction with the outside world is 0. I would have a London dispersion force with the outside world. The London dispersion force came from which kind of interaction? What kind of bond? Non-polar covalent. If we take our straight line of those colors and roll them back on each other, we can see where those connections are coming from. A non-polar covalent bond is going to result in a very weak force. Why? the nonpolar covalent bond has such a strong attraction with its atom that there is no reason to interact with anything else. So its outside force interaction becomes negligible. Okay? Are there other things that we could look at? Well, we had polar covalent bonds. What could polar covalent bonds become? Or where did they come from? Okay, polar covalent bonds generated a dipole-dipole force. Okay, is that dipole-dipole force weaker or stronger than the London dispersion? It's a stronger force, so it shows up a little bit higher up on our spectrum. Okay. Why is it a stronger force? What about the polar covalent bond means that that now has to reach out and find something else? Right? This is a horrible analogy, but if we just did that, now what would my potential interaction be with the outside world? Higher. Why now all of a sudden higher?
Because you don't got a woman.
Now I don't have that other partner. Okay? That connection isn't there. So what am I doing? I'm looking out for other connections. In those other connections, are they official all the way to the marriage end? No. So if you're dating someone, but you aren't married, what might happen?
Trade up. It breaks.
Trading up is the wrong word choice.
It's wrong.
Okay?
Not at all. I'm just playing.
But you might decide, and it doesn't have to be, we look at trading up, it could be both sides of that doing that, yeah. Okay? You could be deciding that that connection doesn't work out and you need a different interaction. Okay? So that connection was a slightly weaker connection than the full covalent bond, which means what are you looking for? Other connections in the world, which means we end up with a stronger connection to the outside world than in the case of the London dispersion. Kind of makes sense? Okay. And then the last one, we've got our ionic forces. Why is the ionic force confusing when we compare it to the ionic bond? They're at the exact same point in our diagram. The difference between a bond and a force is negligible. We're floating on a gray area within a gray area to define the difference between those. That becomes difficult to differentiate them, and we end up labeling bonds and forces almost indiscriminately when it comes to electrostatic. Because that transition between bonds and forces is now massively gray area because we're literally in the gray area between those. That's where we've placed the ionic bond and the ionic force.
So this is like one of those official speed dating situations.
Yeah, we want to go all the way out. It's straight up speed dating. Okay, you're just running through all possibilities.
For the record, I have the underscoring of this entire lecture as Beyonce's "If You're Lucky You Should Put Me On." So, in case anyone else is having a problem right now.
Yeah.
It's been 10 minutes. I can't get it out of my head.
So the idea is to see those interrelationships. That's the point of this diagram, is to see that we're on different sides of it. There are things that need to be altered in the visual aesthetic of that information. For instance, the red, I think, should continue all the way through. I do also think that there should be the straight line definition up to the top. Okay, but what this is trying to do is show the one-for-one parallel. If you have a nonpolar covalent bond, that's going to generate London dispersion forces. If you have a polar covalent bond, that's going to generate dipole-dipole with the option to hydrogen bond, if those extra rules are satisfied. Kind of makes sense? Okay. The last point I want to address on this, for those of you that have to move forward into 151 or further on, if I have a polar covalent bond, I do generate a dipole-dipole force, and that is going to be my primary focus on how it interacts with the outside world. Do I also have London dispersion? Yes. The London dispersion force is just saying, do you have electrons? Well, if it's a chemical compound, what does it have? Electrons. So if you have electrons, you have London dispersion forces. We can typically ignore it because we have a stronger force in the dipole-dipole. This would be like going up with, because we did this before, let's see if we can adjust it, because we did the mountain, let's avoid that, a Tyrannosaurus Rex versus a 5-year-old kid. Okay? In that fight, you would probably choose the 5-year-old kid, because the Tyrannosaurus Rex you're probably going to lose against. But if you were now 5 million tiny little kids, you might take on the Tyrannosaurus Rex, because eventually those 5 million kids are going to overwhelm you. Okay? They're all weaker, but the amount of them changes our perspective on it. Does that make sense? Strength and amount dictate. So what do we do with these? Well, we've got a list of things: phase transitions, vapor pressure, viscosity, surface tension, solubility, and reactivity. Right? There's a myriad of other physical properties that are all dependent back on looking at bonds and forces. Okay? To give you an idea, reactivity, my home, OChem, organic chemistry, we're looking at reactivity for an entire year, 2 semesters. What dictates how those things react? Bonds and forces, that's it. All you're doing is looking at bonds and forces for a year to predict reactivity. Okay? The sooner you can recognize that information, the faster you move through the content. Okay? Solubility is something that you're going to have to deal with. Okay? The ability for something to dissolve in another substance. Okay? That has to do with being similar forces. If the forces are different, they don't interact, which means they don't mix. They don't dissolve. Surface tension and viscosity, your textbook talks about, we won't. Vapor pressure, the ability for a substance to go into the gas phase almost instantly. Okay, what's preventing it from going into the gas phase? Forces. The boiling point, okay, which is also getting at our phase transitions. It's the strength of the intermolecular forces. If I have very strong forces between those individual compounds, what happens to the boiling point? It goes a lot higher, because now I have to put in a lot of energy to break those forces. Okay? So coming up with a way to rank the forces and be able to look at a formula and say, I know that those forces are going to dominate based off of how they can tie to the bonds, is what's going to drive your analysis. Okay? So, which compound has the higher melting point? Okay. These are in reverse difficulty. So let's start with 4. Okay. So higher melting point. What does higher melting point mean to you? Don't go there yet. Too far. Higher melting point means what? It's going to take more to melt. Why is it going to take more energy to melt? Okay. Something is stronger. What is stronger? We have a stronger force. If you have a stronger force, what does that mean about the bond? It's probably ionic. Okay, I'll accept that, but what does that mean about the bond? And don't tell me what the bond is. Is it a stronger bond? Is ionic stronger than our nonpolar covalent? I wish I had that straight line thing that we could look at. No. The ionic was right in the middle. Nonpolar covalent bonds are stronger than ionic bonds. So when we're looking at a stronger force, we're actually looking for a weaker bond. Okay? Why do we have to go to bond? Does anybody see the forces listed here? No. Okay, so what we have to do is look at the structure to evaluate the bonds to then decide what the force is. Once we have the force, we can evaluate the energy, which can get us to the higher melting point. Okay? Which sets us up with the next kind of tricky part. What are the bonds present in 4A? As a hint, there are 4 of them.
Yeah, bonds are first. Which one did you say?
Bonds. What are the bonds present? Hydrogen bond is always an irritating one because what is hydrogen bonding?
But you do have one hydrogen.
Separate question. What is hydrogen bonding?
It's supporting oxygen.
Polar covalent is sort of appropriate, but it's kind of a dodge to the question. What is hydrogen bonding? What is dipole-dipole? What is hydrogen bonding? As a hint, the name hydrogen bonding is a misnomer. What is hydrogen bonding? It is an interaction, I'll accept that. Which interaction is it? It's a force. So when I asked for bond, why am I giving you a hard time, Christian? You've labeled the force, okay? Is the force important? Yes, but again, I want you to move through the sequence. Start at your bonds, move to your forces, move to the energy, move to your answer, okay? You should be moving in that sequence. So your jump was awesome and phenomenal and correct. Slow it down. What are the bonds present in 4A? So as a hint, carbon to hydrogen, carbon to carbon, carbon to oxygen, oxygen to hydrogen. Does everybody recognize that those bonds are present in that formula? Yes. You need to be able to look at that formula and come up with those bonds. This kind of ties back to Lewis structure. I would make the argument that this is a step above what you guys need to be able to do for this class, but it is the expectation in the class. Okay? So, carbon to carbon, what kind of bond is that?
It's non-covalent.
That is a non-polar covalent bond. Carbon to hydrogen, non-polar covalent. Carbon to oxygen, polar covalent, oxygen to hydrogen. It is not hydrogen bonding. What is the bond? It is a polar covalent. A polar covalent bond has what, or sorry, non-polar covalent bond has what type of force? London dispersion force. A non-polar covalent bond has a London dispersion force. A polar covalent bond has a dipole force. A polar covalent bond has a dipole force. As soon as I have a dipole force, what should I consider? Do I have hydrogen bonding? To have hydrogen bonding, what must I have? A dipole force. That's why we're now asking it, because we came up with dipole. What's the next condition? We must have hydrogen bound to oxygen, nitrogen, or fluorine. Carbon to oxygen. Does that satisfy? No. Does oxygen to hydrogen? Yes, which means hydrogen bonding. Because the simplest answer is just to look at the strength of the force, we will start there. Which of those forces do you think is most important? Probably the hydrogen bonding, because it is the strongest of all of the forces listed for that compound. Now what do we do? The same thing for 4B. Carbon to carbon, carbon to hydrogen, carbon to oxygen, oxygen to sodium. Carbon to carbon, carbon to hydrogen. Are those any different than what we had before? No. Because there is no difference, we could cross those out. Is carbon to oxygen different? No. So we could also cross those out. That was me attempting to cross those out. Okay? Oxygen to sodium. What kind of bond is that?
Ionic.
That is an ionic bond. How do you know it is ionic? That's a metal to a nonmetal, which leads to what kind of force? Electrostatic or ionic? I'm going to write ionic because it's shorter. Sorry. Okay. Which force is strongest in that compound? Ionic, dipole, dipole, London dispersion. Ionic. Which is stronger, ionic or London dispersion? Ionic. Based off our answer, we wanted the weaker bond, ionic, stronger force, ionic. Which of those two compounds has the higher melting point? Second one. B. Make sense? Okay. I expect you to be able to come up with 2 and 3 on your own. We will start with 1 on Thursday.